Hey folks, in this video we're going to use universal gravitation to talk about orbit and Newton's synthesis and what does that mean, right? All right, so let's talk about orbit first. So let's say here's the Earth and let's say here's a rock. Well, if you just drop the rock, it's going to fall and hit the Earth, okay? Well, what if you throw the rock? What if you give it a little throw? And let's say you throw it so it's tangent to the circle that would go around the Earth. If you throw it kind of slow, it'll go kind of like this and go plop, right? Well, if you throw the rock faster, if you throw it faster, it'll get farther before it goes plop. And if you go faster yet, and it gets a little farther before it goes plop. Well, if you throw the rock fast enough, it will fall all the way around the world. Now, notice it's falling, but it's falling around the Earth because you've thrown it so fast. It's kind of like it keeps missing the Earth because it's going so fast. Well, that's orbit. Now, if we were to draw an FBD of the spacecraft, here's the Earth. Let's say here's for instance, the International Space Station. Well, the only force after you've thrown it, the only force acting on it will be the force of gravity from the Earth. Okay, so that's your FBD, real tough, right? And by the way, we talked about this in an earlier video. The ship is moving tangent to the circle. If there was no force of gravity acting on it, the ship would keep going tangent to the circle and never come back. Okay, so the astronaut's weight and the ship's weight is what keeps it in orbit around the Earth. And as I demonstrated in the previous video, the force of gravity up there is about 90% of the force of gravity here on Earth, so it's not much less. And that's what keeps the astronauts in their orbit. So how fast do you got to throw that rock so that it goes in orbit? Okay. Well, we're going to set net force equal to ma. We've got our FBD. The only force acting on its gravity. So big G, mass of the Earth, mass of the ship over r squared. Now remember, r is from the center of the Earth to the center of the ship. So in this particular case, we'll have to add the radius of the Earth to the height above the Earth's surface, get our total r there. Well, this equals ma. So this is mass of the ship. That's what's doing the orbiting. And a is, well, it's going in a circle. So a is v squared over r, and that v is what we're trying to solve for. Now, if we do this, the mass of the ship cancels out. So it doesn't matter if it's a ship or a car or a person or a Mack truck or a moon. They all have to go the same speed. Also, one of these radii cancel out. And if you square root both sides, you get v orbit. Now, this is only true for circles. Okay, so if the object's going in a circle, this is your equation for v orbit. Square root of big G, mass of whatever you're orbiting divided by r. Okay. Now, just to plug and chug in here, if you were to plug in the International Space Station, so you need the mass of the Earth, and this would be the distance from, so if we do International Space Station, r would be the radius of the Earth, which is 6.38 times 10 to the 6 meters, plus the space station is approximately 211 miles, which would be, you got to multiply that by 1609 meters in a mile to get meters. That would be your r that you'd plug in there. And again, for m, you'd plug in the mass of the Earth. And for big G, it's 6.67 e negative 11. You get the following. You get v orbit for the space station to be about 7,698 meters per second, which is just a hair under 17,000 miles per hour. So right now, those astronauts are moving at 17,000 miles per hour around the Earth. Crazy number, isn't it? Now, how about our asteroid? Let's say you were standing at the edge of this asteroid right there, and you were somehow anchored to it, because if you were actually standing on it and even moved at all, you'd fly off. So you're somehow anchored to it, and you want to throw a rock. And you want to throw a rock so that the rock orbits the space, or the asteroid, and comes back and hits you, and you catch it. So how fast would you have to throw that rock to put it into a circular orbit that would then come back and hit you? All right, well, the numbers, it'd be the same equation. The difference would be your mass. You would plug in this number down here, your 3.58 times 10 to the 10th kilograms. And for radius, you plug in 270 meters approximately. Okay, that's about the distance from here to here. If you did that, so V orbit for the asteroid is approximately a very small number. You get 0.0940 meters per second, which, by the way, is about 0.2 of 1 mile per hour. So you ain't got to throw that rock very fast to get it into orbit, right, on the asteroid. On the Earth, you got to throw a rock really fast to be in orbit because the Earth is so massive. On the asteroid, not so much. Okay. Now, the next thing I want to talk about is how long would it take for the space station to go around the Earth and also this rock to go around the asteroid for you to catch it. Now, one way to do this is to use the equation, if we're going in a circle, v is 2 pi r over t, and you could solve for t. But here's what we're going to do instead. We're going to put these two equations together because they're both measuring the velocity of that circle, and we're going to kind of solve for t in a certain way. And let me kind of explain. So if I set these equal, 2 pi r over t equals square roots of g, mass of whatever you're orbiting, divided by r. Okay. Now I want to get rid of my square roots, so I'm going to square everything. So I get 4 pi squared r squared over t squared equals gm over r. And then I'm going to do a little bit of rearranging here. I'm going to put the r up there. I'm going to put the 4 pi squared down here. So I get r cubed over t squared equals gm over 4 pi squared. And the last thing I'm going to do is flip this. So we got t squared over r cubed equals 4 pi squared over gm. Now, what is this? What am I doing here? Okay, well, this is called Newton's synthesis. Okay, now, if you look at this carefully, it should look semi-familiar to you. Remember Kepler's third law, t squared over a cubed is a constant? That's basically what we've got here. T squared over r cubed is some constant. Now remember, this constant is, well, there's a gravitational constant there, and the mass of whatever you're orbiting is a constant. So this is indeed your constant, okay? So what Newton did was he synthesized Kepler's third law. Now let me explain a little bit, okay? Notice that Kepler was in the late 1500s, early 1600s. Newton was about 100 years later, okay? Well, Kepler, how did he get his third law? Well, he just guessed and checked, and he eventually came out with, without a calculator, by the way, which I still find pretty incredible, he eventually came up with this relationship that the time of a planet to go around the sun divided by how far it is from the sun, average cubed, is a constant for all the planets. It's the same number for all the planets. Well, Kepler comes around 100 years later, roughly, and he gets the same relationship. But he did it a totally different way. He used the laws of physics to get it. He didn't guess and check. This is all laws of physics that he's using, his own laws of physics primarily. So Newton synthesized Kepler's third law. And when Newton did this, Newton knew that his law of gravity must be correct because he was getting a result that was already known a totally different way. If you and your friend both do the same problem, but you do it in two different ways, and you both get the same answer, you're probably both right. Okay, so Newton knew he was right when he got what in essence was Kepler's answer. Okay, now if you plug these in for the International Space Station and you solve for time, okay, you get approximately, at least I got approximately for period, I got about 5,485 seconds, which is roughly 91.4 minutes, or about an hour and a half. So the astronauts in the International Space Station orbit every hour and a half or so of the Earth, which means they kind of see their sunrise and sunset about every hour and a half. Okay. For the asteroid, you get something like this. So for the asteroid, you get a period of, if you threw your rock just right, it takes about, check this out, 18,039 seconds, which is approximately 300 minutes. which is, of course, about 5 hours. So if you were on this asteroid and you threw the rock just right so it achieved a circular orbit, it goes really slow, and about 5 hours later, you would catch it. All right. Now, the one last thing is I got a sample problem for you. I'll put that in the next video. The sample problem, I'm going to suggest really hard that you try it yourself before you watch me go through it. So I hope this video was helpful, and thank you very much.